Hi everyone, welcome to another CPPC seminar. Today I'm delighted to introduce Zara Bagdasarian from UC Berkeley. So Zara got her PhD from the University of Cologne and Tbilisi State University before moving to a postdoc at Zurich Forschungszentrum, and then moved to her current position at UC Berkeley. So Zara is a neutrino experimentalist. She's an expert on solar neutrinos and the detection of neutrinos, and she's going to give us a tour around a wide range of novel ideas in the field of neutrino detection. So thank you very much again for being with us, and take it away.
Thanks a lot for the invitation. I'm happy to be in Sydney virtually, and as everybody, I think, can't wait to get back to travel and seeing people in person. Thanks a lot for the introduction. And I will start with the general comment that I think everybody's already familiar with neutrinos and familiar that we're surrounded by neutrinos. And indeed, neutrinos don't come just from one source, but we are surrounded from neutrinos that are originating in the core of our sun, that are born in the radioactive decays of our home planet, but also, for example, in such a extreme environments like supernova bursts or active galactic nuclei in the sector of galaxies. This provides us with the unique opportunity that gives birth to neutrinos across a huge energy spectrum, and also at very different distances from where we can detect them here on Earth. That allows us to have the neutrinos as the unique messenger from these extreme environments that maybe no other particle can bring information from. Moreover, we have the man-made sources of neutrinos that give us additional handle on the generation of neutrinos and have more information about the energy of the neutrinos and the exact distance from their generation to the detection. That allows us an extra handle to learn about the neutrino properties. We can learn a lot already from the natural sources, but man-made sources can also give us even more information. So we have these neutrinos that are coming from all around the place. And in order to actually detect them and get the maximum information from the astrophysical objects and the neutrino properties, the fundamental building blocks of our universe, we need a wide variety of detectors. And as Cherenkov already mentioned, it takes quite an effort, and I will take you across the globe at different locations where different detectors are already built or being built for tackling different questions in neutrino physics. I will start with the Borexino experiments and with the highlight of the 2020 results on the CNO neutrinos, and then I will continue with the novel technologies that allow us further improve our access to neutrino physics. So in times before COVID pandemic, we could easily take a flight to Rome, and just 80 miles, 130 kilometers from Rome, you find this beautiful lab under the beautiful Gran Sasso Mountains, known as Laboratorio Nazionale del Gran Sasso. Here, there are living a lot of experiments for neutrino physics or dark matter search, where we really are looking for the very rare events. So this mountain above the lab helps us to reduce the cosmogenic background by 1,000,000-fold. One of these detectors is Borexino, and it has been taking data from 2007. And its qualifications include unprecedented scintillator radiopurity, low energy threshold, high light yield, and generally good energy and position resolution. These kind of qualifications allowed Borexino to make a really groundbreaking measurements in solar neutrinos and geoneutrinos, but also tackle questions of physics beyond the standard model. The channels of neutrino detection are elastic scattering for neutrinos and inverse beta decay for the antineutrinos. The weakness of Borexino is it is relatively small for a neutrino detector, around 300 tons of active volume. And with using the scintillator detector, no directionality has been extracted from the detector. So definitely the purpose with which Borexino was built, but also what it's most famous for are the solar neutrinos. Our sun is fueled by the fusion of the hydrogen into helium, and along this process, there are born the positrons and neutrinos. And these neutrinos, we actually refer them not just one, say like all of them are solar neutrinos, but we can actually distinguish them from which fusion reactions they actually originated. And that's why we are calling, for example, the neutrino that was born in the first step of this proton and proton fusion, PP neutrinos. And for example, here, the neutrino born in the decay of boron 8, we would call them boron 8 neutrinos. Each of these neutrinos are born as electron neutrinos, but they are specified by the particular energy range. And what we see here, for example, is the flux of these neutrinos coming from different fusion cycles as we see them here on Earth. Borexino is a scintillator detector, so it was able to push the threshold of the solar neutrino detection very low, and where we can actually see each of the interaction basically in real life. This allowed us to have this very precise measurements of the different reactions in the PP chain reaction, which constitutes around 99% of the solar energy production. And we went from the very first time measurements of, for example, beryllium-7, PP, and PP neutrinos to precision measurements that we managed to one go measure, for example, the beryllium-7 flux with less than 3% error, PEP with the 20%, and PP with 10% error. And this result was published in Nature in 2018. This kind of precise measurements allow us to tackle both the physics of sun and also the neutrino physics, because we have the fixed distance between the sun and the Earth, and we know where it's originating from, and we can learn a lot about the neutrino properties. And that's actually historically probably what solar neutrinos have been most famous for, that the solar neutrino problem resulted in us knowing what the neutrino oscillations actually take place in the world. But even if we actually already accounted for almost 99% of the energy production in the sun, this less than 1% is a very interesting process because it happens via this CNO cycle, which stands for carbon, nitrogen, and oxygen. This may be maybe less than 1% in the sun, but it plays much bigger role in the heavier stars. And since there are a lot of heavy stars in the universe, actually CNO cycle is the primary mechanism for the stellar conversion of hydrogen into helium in the whole universe. So just the fact that we actually in 2020 measured it for the very first time, and now it goes not just the reactions that somebody wrote with the pen on paper, but we actually experimentally measured it. It's a big thing for astrophysics in general, because we can actually see that it happens in the sun, it must happen in the other stars. For the solar physics, it's also very, very important because this small flux is actually the most sensitive to the so-called sun metallicity. Metallicity is called, so astrophysicists call metals any chemical element that is heavier than helium. So it's basically the abundance of these heavier elements in the sun. And the metallicity of the core of the sun is actually still a very open question. And we have some conflicting models of standard solar model that struggle to describe all of the data that is currently available. So measuring the CNO neutrinos that are the most sensitive to those different models can actually be a game changer in the future of solar physics. So if it is so important, you ask, why haven't we measured it before? It is definitely was very challenging to do so. First of all, it's as I mentioned, it's less than 1% of energy production. That means it's a very low rate of the neutrinos coming from this process. So we expect to have only 3 to 5 interactions per day per 100 tons of the active material. And that, for example, I showed you that we distinguish different neutrinos originating in different fusion reactions by their energetical spectrum. And the fact that it happens to be so that the CNO neutrino spectrum is actually pretty similar to that of PET neutrinos and the internal background of bismuth-210. This is why we, in order to actually make the measurements, we need to put the constraints on the other components to exclude the strong correlations. For the PET neutrinos, it's actually pretty easy to do because you have the solar luminosity constraint, and we can put a very stringent constraint. And for bismuth-210, we can do it thanks to a smart link and the nature kindness because it's linked with the polonium-210. So here you can see the decay chain of lead-210, and you can see that, for example, bismuth-210 has a lifetime of around 5 days, and it gives birth to polonium-210. There's also a radioactive element, but it decays an alpha decay. And the fact that it's an alpha decay helps us, first of all, that it's a monoenergetic process. That means that we will have a very distinguished Gaussian peak around the energy of the decay, but also we have an additional handle to distinguish alpha particles and the beta particles happening in the detector. Moreover, so these are the advantages, but there are also some challenges with polonium-210. If there is contamination of the lead, for example, that is on the vessel, and it decays to bismuth-210, since bismuth-210 lives for only 5 days, it will actually not reach the center of the detector. It will diffuse before, it will decay before that. But polonium-210 has around 140 days lifetime. That means it actually has enough time to enter the center of the detector. And what we have observed during the long data taking of Borexino, that we saw that actually very seasonal, strong perturbation. So we would see more polonium in summer on top and less in the bottom, and the opposite situation in winter. So in order to create this kind of space in the detector that would not be disturbed by the additional polonium-210, we need to create a thermal insulation that will stop these convective motions in the detector. So then you can have a quite stable value of the polonium in the center that is really originating only from the bismuth that is in this volume, so in intrinsic volume inside this liquid scintillator, and we can have some of additional polonium that still manages to detach and slowly move towards the center of the detector. This campaign of the thermal insulation of Borexino, we often call it that Borexino got an astronaut look. So it involved 2 layers of wool that would isolate the detector from the environment, and also a lot of sensors have been installed to actually control properly the temperature of the detector. As a result of a lot of work in hardware and software development to visualize it, we have actually observed that there was created this kind of volume with the low polonium-210. It's around 20 tons, and it's located a bit off the center at 80 centimeters above the equator. From the volume, from the value that we got of this polonium-210, we can put the conservative limit on bismuth-210, because there can still be some of the polonium that detached from the vessel and slowly move to the center. But if we attribute all of this polonium to only bismuth, this is the upper limit value. And we got the number of 11.5 counts per day per 100 tons of the liquid scintillator. So what, okay, so we mentioned that we have the constraint on the PAP neutrinos. We got the value of bismuth 210. But of course, there is, even in the most radio pure liquid scintillator in the world, there are still other backgrounds. So first one, that's a very interesting background, is the cosmogenic background. That means that the muons that manage to survive the mountain of Gran Sasso and penetrate the detector. Since liquid scintillator is an organic liquid scintillator, so it's mostly carbon, muon can interact with carbon and create carbon-11 isotope and the neutron. The neutron can be captured with 250 microseconds, but carbon-11 requires around 30 minutes lifetime to decay. And if we would completely veto it, it would take quite a lot of our exposure. So what we do is we actually split our data into two parts. One, when we actually take the volume where you actually have a very low probability to have carbon-11, and that constitutes around 63% of exposure. And then you have the part where you have quite a lot of carbon-11. Sorry. So we concentrate this 95% of carbon-11 in only 36.4% of exposure. But the interesting trick is that all other components, they don't change based on muon has passed in the detector or not. So we can still perform the feed assuming that all other components will actually be the same in these two different exposures. These other components can be internal backgrounds. So the thorium and uranium are actually negligible in Borexino, but we have, for example, krypton and bismuth we have already mentioned, and polonium 210 we have already mentioned in details. Finally, yesterday's Signal and Nature paper is today's background. So PP chain neutrinos like PP, beryllium 7, and PAP neutrinos are actually treated as the background here. Putting all these values and putting constraints only on this PAP and beryllium bismuth 210, leaving all other components free in these two exposures, and just adding up also the radial distribution to distinguish between the uniform components and the external backgrounds. We can perform this multivariate spectral feed, and we obtain the value of the CNO neutrinos with around 7.2 counts per day per 100 tons. Of course, the statistical error is actually still pretty big. And here you can see the mean value of this 7.2 that I mentioned, but you can see also the full likelihood spectrum without the systematics with this dotted line, and including the systematics with the solid line. And you can see that it's the systematics is actually quite small, and the biggest the systematics contribution is coming, as one would expect, from this bismuth 210 constraints. In addition to this multivariate spectral feed that I have described, we also have performed a bit simpler counting analysis result, where we choose the region of interest in the energy, and we very conservatively assume different constraints, so bismuth 210, PAP neutrinos, other components that might contribute to this region of interest. And what we find, there is still plenty of room for the CNO neutrinos. So this result you can see here in red, and it's also comparable to the multivariate fit results with a bit less significance, but the values are consistent. With the multivariate fit results, we disfavor the hypothesis of no CNO neutrinos with more than 5 sigma significance, and that contributes the first discovery of neutrinos from CNO fusion cycle. As I mentioned, it is one of the main motivations to measure CNO neutrinos is the metallicity question of the solar core. And this is what, and I mentioned that there are different solar models. And this is what here I show in this purple and blue. HZ stands for high metallicity models, and low Z stands for, LZ stands for low metallicity. And you can see how this, these two bands, so the mean values with 1 sigma bands, compared to the results that we have currently measured in Borexino. So we are not at the stage where we could statistically disfavor one model or the other, but potentially if one would narrow down the uncertainty on the CNO neutrinos, one could make an important contribution to the metallicity. In the meanwhile, the astrophysicists are also, of course, working on refining their models and hopefully also reducing their uncertainty on the predictions of low and high metallicity. But Borexino has done actually even more than measuring just the solar neutrinos from PP chain and the CNO neutrinos, which is not a small feat. But it's also, for example, made one of only 2 measurements in the world of geoneutrinos, that is the neutrinos that are born in the radioactive decay inside the crust and mantle of the Earth. And this paper has also been published in 2020 with quite a lot of details, and we are looking forward also to many other experiments contributing to this interesting field. But there are also, Borexino is part of a new system that is working on the search for supernova bursts and have also performed searches for correlations with gravitational waves, gamma rays bursts, and there was even the project for the sterile modification a bit of Borexino detector to do the sterile neutrino search, but that has been canceled later on. The searches beyond standard model have included the deviations from Mihev-Smirnov-Wolfenstein effect, non-standard interactions, and the search for neutrino magnetic moment. So the Borexino was as I hopefully convinced you, has been a great experiment that has been running since 2007. It's still taking data, and it has made the huge contribution in solar physics, but also touched on other questions in neutrino physics. So now looking into the future, let's take a look about what other novel technologies can provide new opportunities for the probing fundamental questions and applications in neutrino physics. So first of all, I have already, let's start with a bit of the principles of neutrino detectors. And I have already mentioned a bit in the context of Borexino, the scintillator. And so the scintillator detection, so the scintillator material is a luminescent material that absorbs energy of an incoming particle and then remits the absorbed energy in the form of light. So this is characterized by high number of the scintillation photons per EV of the absorbed energy. And this is what allowed, for example, Borexino to go to the very low energy threshold and probe the PP solar neutrinos, for example. On the other hand, we have quite a lot of detectors around the world that are based in a different detector principle, the Cherenkov detectors. You might be familiar, for example, with the Super K, with a huge water detector, or ice cube in Antarctica. So the principle here is that the incoming particle with velocity greater than the speed of light in this material emits light similar to a sonic boost. And the angle of the emitted light cone is actually a direct measure of the particle speed. This is a very interesting process, and it definitely gives us advantage of the direction, but it also has some disadvantages. For the Cherenkov detectors, for example, as I mentioned, they can be built very large. And but for example, we don't have the access to physics below the Cherenkov threshold. So until this process actually happens, but even if it happens, we need quite a lot of energy to actually start seeing the events. So that's why it's characterized by relatively low light yield. On the other hand, the scintillation detectors like Borexino or Snow Plus now have actually high light yield. So as we said, like they produce a lot of the scintillator photons, but they have, and we can achieve low energy threshold, good energy and position resolutions, but they are limited in size by absorption and also cost, which is also not something that we should forget when designing a new experiment. So we try to combine the best of these two worlds and look at the created detectors that will be based on the water-based liquid scintillator. To give you some basics of this concept, water-based liquid scintillator is a mixture of pure water and oil-based liquid scintillator. As you might know, the water and oil don't mix that well. So you actually need a bit more complicated chemistry. You add surfactants, which are soap-like structure, and they help you hold the scintillator molecules in this kind of missile structure. And using this great chemistry, we can actually combine the advantages of water and liquid scintillator. So the fact that also this, by combining these different detection techniques, we can extract much more information from any given event. And here we're also quite lucky because the nature of these two processes is quite different. It allows us to actually separate the two processes. So for example, we mentioned that the Cherenkov light is very directional light, while scintillation light is uniform. So just looking at the angular resolution, you can already distinguish pretty well where the Cherenkov light is and where the scintillation light is. As I mentioned, the scintillation is the re-emission of the light. That means that you have some timing delay, while Cherenkov light is basically instant. So you can look at the timing of the events and also try to separate where's the Cherenkov light coming, where's the scintillation. And here's, for example, it's quite interesting to look at the new developments in the photodetectors, such as LAPPDs, which stands for Large Area Picosecond Photodetectors. And you can fully explore this timing information. Finally, also the spectral shape of these two processes is also quite different. You can see that the scintillation has a quite strong peak in a particular wavelength range. And here we can actually try to sort this light by their wavelengths and try to separate the scintillation and Cherenkov lights. And here there have been quite interesting developments in dichroic filters in the Penn University, and we also started some experiments here in Berkeley with it as well. So while it's quite, the principles of WbLS are quite simple, and of course we want to combine the best of the two worlds. In reality, it is of course a bit more complicated. So when our chemist collaborators that create a given WbLS cocktail, we need to make quite a lot of measurements of this new material, for example, the light yield, the time profile, and the spectrum, in order to actually see how this new material would behave in real life. So we are creating the Monte Carlo models that we are validating at the small scale, and then we are building the big models for the large scale detectors, where we can explore and predict different impacts of this material at the large scale. So what do I mean when I talk about the large scale? And actually we are having actually quite nice timeline and mass scale, where we, in the exciting future, we are increasing the mass of the WbLS implementation. And we are going, hopefully, increasing with from year to year, and then eventually will be this big detector that can explore quite a lot of things. So I promised you a tour. So after Borexino in Italy, let's travel to Annie in the US. Annie is located at Fermi Lab. More specifically, it's located at the booster neutrino beam, and it has been taking data since 2016, and its main goal is understanding neutrino nucleus interactions. Now, the interest to WbLS development is that Annie experiment actually plans to deploy WbLS volume of around 0.5 ton in the middle of the detector, and that would live in the 26 ton of gadolinium loaded water. And moreover, any experiment, it will be the first experiment that actually deploys this LAPPDs, this brand new photodetectors that I mentioned. And that actually they're being installed right now at Fermi Lab. So it's a very exciting time where all these novel technologies are actually coming into online at the larger scale. So what we plan to do is we deploy this WbLS vessel that is around 1 meter height cylinder. And what we plan to do is actually to test WbLS in the neutrino beam environment. So you have the beam coming from the Fermi Lab, and then we can actually try to separate the scintillation light and Cherenkov light in this environment, and in real life try to work and reconstruct with the high and low energy events. So there, remember, so this is the neutrinos that are coming from accelerator. Now we are moving to the new experiment that is will be located in the UK. And here our main goal is actually to look at neutrinos that are born in nuclear reactors. Now, interesting thing here is that this experiment will actually be the first neutrino application. So its main goal is not the fundamental science, but neutrino application. And what we want to do is to show that we non-intrusively detect on and off power cycle of a single reactor. And while we are showing this neutrino application for non-proliferation goals, we are also developing quite a lot of know-how that would be interesting for the fundamental science. So we could deploy this WbLS material at the kiloton scale, and we can gather a lot of knowledge about the reconstruction of the low energy antineutrinos coming from the reactors. So the Neutrino Experiment One, the NEO, is maybe some of you, if it sounds familiar, maybe earlier you heard about it as Watchman. Watchman is still the name of the collaboration that really is promoting the use of the neutrino detection for remote monitoring and fundamental science. Just to stop 1 second, and actually the advantages of using neutrinos for non-proliferation goals. So currently in the International Atomic Energy Agency, there are already in place a number of safeguard practices at different nuclear reactors around the world. Normally what happens is that operators declare fewer burnup and power history, but but for example, unless the fuel is reprocessed, there is no direct plutonium measurements. Also, there is no way to have the real-time inventory of what is happening in the nuclear reactor. So the neutrinos, as we know, are not so easy to shield. So that's why, for example, neutrinos can be this real-time measurements of the activity of the nuclear reactor. So there have been, of course, some proof of principles that antineutrino detection is possible, and especially like at the short range. But what we are currently more interested is the remote reactor monitoring that could be of interest for non-proliferation. So to give you the current the status of the experiment, we are at the final stages of the design of the experiment. So we have prepared several design studies that are currently under consideration by sponsors, and based on this exploration of different sizes of detectors, the photo coverage, so how many photomultipliers will you install in the detector, we are hoping to finalize the final design of the experiment very, very soon. Finally, the THEIA experiment will be something that brings together all the knowledge that we gathered with the ANI and NEO experiments, and that we can fully build this big experiment that would fully explore both the astrophysical objects, so we're already familiar with solar neutrinos or geo-neutrinos, but also to look more at the neutrino properties, such as neutrino mass ordering or CP-violating phase, neutrinoless double beta decay, for example. So currently there is no final design of the THEIA. We are considering two designs at the moment for our studies. One we would call the baseline, which is 25 kilotonnes, which corresponds to around 17 kilotons fiducial volume. So the volume that you would actually analyze for your analysis, and the ideal 100 kiloton that would translate to 70 kilodon fiducial volume, more or less. So the most probable location for the THEIA experiment, especially that of 25 kiloton, is the, you might recognize the picture from the DUNE experiment. And there are currently so-called the cavern of opportunity that is available, and THEIA is one of candidates to fill it. And that would be very interesting setup for THEIA, because it will allow us to do a long baseline neutrino oscillation measurements. There is around 1,300 kilometers between the Fermilab and SURF. And this would allow precision measurements of neutrino CP-violating phase. And actually, it's very interesting that if THEIA is located next to DUNE, because it will have same location, but different targets, different systematics, and it's important cross-check for measuring such important values as the CP-violating phase or mass ordering. There are a number of experiments currently working with this goal, and I think we will agree that just one experiment measurements will not be enough. We will need to work together and have the cross-checks and combine analysis in order to actually put the final values for CP-violating phase and mass ordering. So for here you can see how THEIA 25 kiloton and 100 kiloton compare, shown in fuchsia compared to the DUNE 10 kilotons. And for example, we you can see a bit more details of this in the white paper that we have published also last year. You can see the link in the bottom of the slide. So the long baseline neutrino oscillations, as I mentioned, man-made source, fixed distance, so we can really explore the neutrino oscillations, and that's very interesting for us, is the CP-violating phase and mass ordering. But as I mentioned, the neutrinos are very interesting for the astrophysical objects, and the supernova neutrinos are of high interest in the field. Currently, we have measured only one supernova, and now it is time for the next supernova that neutrino detectors can measure. And THEIA provides quite interesting opportunities here, because it can show high statistics, low threshold, thanks to the scintillation part. And we can actually work on even the supernova pointing, which can be very interesting for multi-messenger physics. Again, if it is located close to DUNE, it's also a unique opportunity, because we can combine the THEIA measurements with WbLS and DUNE measurements with liquid argon that allowed us at the same site co-detect with very high statistics neutrons with DUNE and antineutrinos with the THEIA. Moreover, so THEIA would be located in the US, and on the other side of the Earth, you have the Juno experiment in China, and the Hyper-K experiment will be built in Japan. So that allows you to measure the same supernova neutrino burst flux on different sides of the Earth. And that we could measure the Earth matter effects, which will be a unique opportunity. Finally, with such a big volume, we can also possibly measure pre-supernova neutrinos, which are again very interesting in order to give a proper warning to other telescopes around the world for where to look when you are looking for the next supernova. Besides the supernova bursts, which of course, like, you know, we have to be lucky to have it when any given experiment is online. We also are surrounded by the diffuse isotropic flux of neutrinos from all supernova explosions in the universe. And this flux is out there, but we have never measured it before. And here it is on the agenda of several experiments right now. For example, like Super-K and Juno. But having this unique handle on distinguishing and co-detecting Cherenkov and scintillation light gives us a powerful handful to discriminate the main background for DSNB, which is the neutral current background from atmospheric neutrinos. So this would allow us a very strong handle. We can see here the dependence on the scintillation and the being able to separate the Cherenkov scintillation light. And that could result in, first of all, principally very interesting measurement that would be a substantial addition to Super-K and Juno, but it will also result in substantial increase in event statistics. And within 8 years with 25 kilotons and around 2 years with 100 kilotons, we can put around 5 sigma discovery on the DSNB neutrinos. Finally, going back to the my favorite solar neutrinos, THEIA has a huge potential to continue Borexino's solar legacy, and we can measure CNO neutrinos with higher precision, and very interestingly, using a different technique for background projection. So, for example, I mentioned that in Borexino, we had to go to quite a lot of hassle to put the constraint on bismuth 210, but with the ability to have both Cherenkov and the scintillation light, you can put distinguish the direction of your initial particle, and hence distinguish in that way the uniform bismuth 210 and the CNO neutrinos coming from the sun. And the different ability to have the directionality directly impacts the uncertainty of the CNO that you can measure. Moreover, also boron-8 solar neutrinos have quite a high potential in exploring new physics. We currently have the measurements with Borexino and also Super-K and SNO, but there is this region that is the transition between the vacuum oscillations and matter-enhanced flavor conversion. And here there is like a lot of potential for new physics. And that's where a lot of theories works are concentrated. So being able to measure high statistics, low energy boron-8 neutrinos is a very interesting handle for the fundamental physics. Concerning the geoneutrinos, the location in the US will be very interesting to be complementary to that of Borexino in Italy and Camelot in Japan. Adding the high statistics because they were much larger than existing the experiments, and also just the fact that it will be different geographical location in the US in comparison to Gran Sasso Mountains and the surroundings of Camelot. Finally, the most ambitious goal of the THEIA is that you can actually deploy a balloon for neutrinoless double beta decay isotope loaded liquid scintillator, and to explore with the same the experiment this very rare process, but hopefully, but maybe it actually exists, where we can actually explore the absolute neutrino masses and also mass ordering, and of course the nature of the neutrino, whether it's Majorana or direct neutrino. You can see some of the sensitivity studies that have been performed, and we are looking at the loading with xenon and tellurium, which are actually also used in several other experiments. And you can see how the THEIA potential compares to the other experiments of the future. And you can see that here again, we are using the advantages of this Cherenkov and the scintillation in order to access this and have this unique ways of tag your signal and from your background. So for example, boron 8 is the solar neutrino, so we know that it's coming from the sun. So by having ability to reduce the boron 8 background bidirectionality, you can significantly improve your reach on the half-life time of neutrinoless double beta decay. Or by increasing the scintillation component, you can also influence the lifetime that you can reach with your experiment. So I know there was a lot of information, so I will try to summarize. So we have the THEIA experiment that has very ambitious goals across the fundamental neutrino properties and the astrophysical objects. And the most probable location for THEIA is that of the dune cavern location. And using the Fermilab's neutrino beam, we can tackle long baseline oscillations that would allow us, for example, to reach more than 5 sigma for 30% of CP-violating phase. We can explore the fundamental physics questions that would possibly allow us to observe the nucleon decay, but also, as I mentioned, the supernova neutrino physics is very interesting with this new novel target material with the supernova for the supernova burst events and also diffuse supernova neutrino background. By making sure that we can reach the lower energy threshold, in addition, we can explore the solar neutrino physics, especially CNOs. The geoneutrino measurements can be a huge improvement on the currently existing ones. And finally, the most ambitious goal is to have the additional loading with the neutrino WbLS beta isotope and to have the lifetime reach that would go like up to 10 to 28 years for this process. To conclude, Borexino has measured both processes that sustain nuclear fusion in the sun, the PP chain and the CNO cycle, but currently we're looking in the future, and the progress that we see in the novel target materials and photodetector technologies open the path for the next generation neutrino experiments. THEIA will exploit the advantages of these developments to achieve the low energy threshold, good energy and position resolution, directionality, and large exposure to tackle a broad physics agenda. On the roadmap to THEIA, we have opportunities to explore these technologies at large scale, and on the way tackle other physics questions and applications with the N experiment at Fermilab and new experiment in the UK. So I would like to thank you for your attention, and of course, thanks to all my colleagues with whom I've been working on these topics, and it's been a lot of fun. Thank you for your attention, and questions are welcome now or later. Thank you.
Great, thank you very much. That was a really fascinating talk. Yeah, you covered a lot of ground there. I have a lot of questions, but maybe I should allow other people, if they have a question they want to ask, to go first. Please just unmute yourself or ask whatever. Don't see anybody, so I'll go first. So I think some people in the audience probably know the question that I most want to ask. So with the directionality for THEIA, I guess you're still in the process of sort of understanding, you know, how this new material sort of behaves. But are you confident that you'd be able to get good directionality down at these solar neutrino energies, or is that sort of something you've made an educated guess about, or are there experimental results that sort of demonstrate that you have kind of a good angular resolution down at those energies? What's the sort of status of the directionality?
That's a very good question, and it's I would say that it's still very much work in progress, right? So there are a lot. We are still exploring the phase space where we are doing a lot of assumptions that we're saying, say we can achieve this angular resolution, what kind of physics we can do with that. And that's also, so we are doing quite a lot of studies in this. And I think it's also, we are still working on it in the sense of guiding the material production, because with using these assumptions and saying like how it would behave in the large scale, we can then still give feedback to the chemists who are producing, and we're like, actually, this part of the this quality is much more important for us than what we originally thought. And the principle, as I said, like with waving hands, it's quite straightforward. You say like, okay, more scintillation, better energy resolution, and more Cherenkov light, more directionality. But when you're putting everything and there's like complicated process, we actually have to explore quite big phase space of this quality. So we don't have right now, and that's the exact value that we can achieve. But that is why we are having all this R&D program now, and why before building THEIA at the large scale, we're having this a bit smaller large scales where we can test a lot of things that we're developing.
So with your sort of intermediate stage with this ANI, where you have this sort of smaller water-based liquid scintillator inside and the neutrino beam, is that the sort of thing you could measure? Could you measure is the neutrino beam at the right energies to be able to
no, so neutrino beam, that's a good comment, that neutrino beam is at higher energies than what you would expect from solar neutrinos. But it's still the first step of actually showing it at the scale.
So I'm. Nobody else wants to jump in, I'll just ask another one. So something you mentioned really briefly that sort of caught my eye was this, I think it was the polonium-210 background in Borexino, you said had this seasonal modulation between like the top and the bottom. Is that just a temperature thing? Do you have a kind of a full understanding of like where that comes from?
Yeah, it's mostly the temperature change thing. So it's the seasonal change in general, like the changes in the lab. So besides that, like so from the data that we are looking at, we also have independent group in the collaboration who are doing the like take the numbers from this temperature sensors that we have, and they are doing the fluid dynamic simulations, and they actually can it was actually, as always, it's always nice to see when two groups are working on something and then they show pictures and they have like a very good agreement. So it's really mostly temperature and the fluid dynamics. It is very complex, but it's still also possible to model, and we are able to do that within the collaboration.
That's good to know. And I guess I mean the CNO I guess discovery is like really spectacular in itself that you're able to do that. But I suppose that the obvious question is sort of, what sort of statistics would you need to be able to distinguish the high metallicity and low metallicity solar models? And at the uncertainties that they currently stand, is that something that's even feasible just with statistics with Borexino, or is it something you really are going to need to go to a larger experiment to be able to do?
Yeah, so the work has not stopped. So as I said, Borexino is still taking data, and there are certainly continuation of the CNO measurements and trying improve the approaches. But unfortunately, just the statistics of like another year or two will not change significantly the uncertainty. So the real main effort is to find alternative ways to work with the data, or that to constrain more significantly. But unfortunately, with Borexino, just statistics would not be helpful. But with the THEIA, for example, where you have like orders of magnitude larger, then you could the statistics could actually help quite a lot. So there are different ideas circulating how you can put more stringent constraints on it, and the directionality is one way that I mentioned in the THEIA, but just the statistics wise, you can also, since it's a very rare process, but if you have a big statistics, you know, that's a beauty of statistics in general, right? So even the rare things, just with a big enough detector, you can actually see it.
Well, we're nearly coming up to the hour, so I mean, people don't have to stick around if they have other things to go. Michael had to leave. I'll ask one sort of final thing. I think I got a bit confused when you were introducing this Watchman, the reactor neutrino experiment. I mean, so I guess the idea is that you have you know, a large neutrino detector close to a reactor, and you were talking about this sort of non-invasive you know, measurement of you know, whether the reactor is on or not. I guess I don't understand why that is important to be able to do. Like, what I mean is, are they sort of trying to do that just as a kind of proof that you can do this with neutrinos, and then it would be scaled up and you'd have some kind of monitoring of all the reactors around the world? Is that the idea?
So the purpose of this one is just the proof of principle, right? So the standoff is 25 kilometers between the reactor and the Boulby lab where it will be built. But the bigger goal is that once you prove the principle, and for example, you have so now, as I said, like there are like more than 200 nuclear reactors worldwide, and most of them are quite transparent about their history and the power cycles and so on. But in principle, you can have a country or a power plant that maybe not as transparent about their the logs of their history, how the nuclear reactor evolves, whether, you know, they may produce some plutonium that's not supposed to be produced there. So this kind of things that maybe they would not be collaborative for like more intrusive kind of monitoring. So that having neutrinos that may be even located outside the country's border allows an additional handle, for example, to cross-check the data that has been provided, or have an independent measurement of the activity of the reactor, and not probably, let's say, not in the near future, but later on, maybe also distinguishing the exactly which component of the nuclear reactor has produced this that many neutrinos. So the first goal is very simple. It's just to detect whether like one core was on or off in a particular period of time. But there is looking into the future, there is a big potential about like getting more and more information about the activity of the nuclear reactor.
Yeah, that's extremely cool. That we're at the point where we can do that. So we're past the hour, so